In this video, we will talk about what a vector-valued function is. So I want to begin by making a table where we sort of organize the lists of different types of functions that we have so far. So the most common type of function that we would have seen is what's called a scalar function. And those are just regular functions that we're used to. So something like f of x equals x squared is just a regular function. It's called a scalar function because the input, the number that you plug into this function, so the thing that you plug in is a number, or another way to say that is it's a scalar. Remember, a scalar is just a number. It's not a vector. And the output is going to be another number. So the output itself is another scalar. So the output is also a scalar here. It's just a number. We have also seen parametric functions. So I'm just going to abbreviate PAR for parametric. We've also seen parametric functions. So an example of that would be something like x of t equals root t, y of t equals t, and z of t being equal to t squared. So that's an example of a parametric function. Okay, so the input here is a number. We're going to input a number in for the t. That's what we plug in a value for t. But the output now will be a point because we get an x coordinate, a y coordinate, and a z coordinate in the example that we just gave. So in this section, we're going to introduce what are called vector valued functions. Or sometimes for short, I'll just call them vector functions. So an example is, so I'm going to introduce some notation right now. When I write a vector function, like r of t, I put a vector arrow on top. That's how I indicate that it's a vector valued function. So that when I plug something into a vector valued function, I need to get out a vector. So I'm going to put this in component form. So I'll just do square root of t first, and then comma t, and then comma t squared. So I've basically just taken my parametric function from the last example above, but put it into vector form. So in this function, I'm still plugging in a number for t, but my output now, actually let's write that in blue. So we are still plugging in a number, in this case something in for t, but what I get out is now a vector. And the fact that I get out a vector is what makes this a vector valued function. All right, so let's do an example where I try to motivate why we might be interested in having vector valued functions and what they can do for us. So here's the example. A particle is moving along a parametric curve according to the equations x equals t and y equals 4 minus t squared. All right, so the first thing that I'm going to do is I'm going to try to graph this and draw the motion of this particle. So I'm going to draw some axes, and I'll make a table of values to determine the direction of this particle. Okay, so before I get into the table of values, I can actually quickly get an xy equation for this. So I know y is 4 minus t squared. But based off the first equation, we know that t is x. So once I substitute that in, once I substitute x in for the t into the second equation, we get 4 minus x squared. So the curve that this particle is moving along should be the curve 4 minus x squared. So we're talking about a upside down parabola like this. Oh, whoops. So an upside down parabola, and the vertex is at 4 on the y-axis. Okay, so I'm also going to plot some values here to figure out what's the direction of this particle. So I'm going to plug in -1, 0, 1, 2, and 3 in for the t. So x is the same thing as t, so the x values are also going to be the same. So -1, 0, 1, 2, and 3. And when we plug these values in, when we plug these t values in to the equation for y, so we get the following. So if I plug -1 in, 4 minus -1 squared is going to be, that's going to be 3. If I plug 0 in, 4 minus 0 squared is 4. And I'm going to do the remaining ones more quickly. So plugging in 1, we'll get 3. Plugging in 2, we'll get 0. And plugging 3 in for the t, we'll get -5. Alright, so if we start to plot some of these points, so when t equals -1, we're at the point -1 for x, and the y value there is 3. So this is where we are when t equals -1. When t equals 0, we're at the point 0, 4, which is the top of the parabola here. It's the vertex. When t equals 1, we are at 1, 3. That's this point. When t equals 2, we're at the point 2, 0. So that's on the x-axis. So t equals 2. And then t equals 3 would actually extend really, really far down somewhere. Maybe not that far down, but it would be like somewhere here-ish, I think. T equals 3. It's significantly lower than the other points have been, because the y-coordinate dropped all the way to -5. Okay, so the direction that my particle is moving in is this way along the curve. So I'm drawing in some direction arrows to indicate what direction this particle is moving. So a question that we might be interested in answering is, well, is the particle moving faster at t equals 1 or t equals 2? So when we have parametric equations, we might be interested in comparing or knowing something about the speed of the particle, how quickly it's moving. So the way we can try to answer this is to look at the related vector valued function. So there's a related vector valued function I could set up for the position of this particle, but in terms of vectors. Okay, so I'm going to call this vector valued function r with a vector arrow on top of it, r of t. And what I'll do is I'll take our two equations that we had for x and y, and I'm going to make them the components of this vector valued function. So the x component is t, so I'll write t, and that's going to be the I component. And then the y value is 4 minus t squared, and I'll have 4 minus t squared times j hat, and that'll be the other component. I can also write this in just component form in brackets, so this would be t for the first component, and then 4 minus t squared for the second component. So I can also write it like that. So r of t, r is typically the variable that we use to indicate position when we talk about a position vector function. So ultimately, we're going to answer this question about whether the particle is moving faster at t equals 1 or t equals 2, ultimately in the next video. But I wanted to just frame this question now so we have a goal to work towards. So now I can build up some tools to work with these vector functions, to work with this position vector function, so that we can answer something about the speed. Alright, so what I want to end this video by doing is just plugging in some values in for the t into this vector function, and then draw what it is that I'm getting out. Alright, so I've just gone up to the top of the page to give myself some more room. So here's our vector valued function for position. If I write it in component form, we get t for the first component, and then 4 minus t squared for the next component. Alright, so what I'm going to do is I'm going to draw some axes. And I know that this position function corresponds to the equation y equals 4 minus x squared, because that's where we derive this position function from. It's from the equation of the parabola. So I'm going to draw the parabola. And now I'm going to plug in some values of t into this vector function. So I'll plug in -1, I'll plug in 0, I'll plug in 1, 2, and 3. So all the values that we were plugging in to the parametric function that we had before. So if we plug -1 into this, I'll get negative I hat, and then plus 3j hat. If we plug 0 in, the I component goes away, and we just end up with 4j hat. I'm deliberately putting space there so I can keep the j components all sort of aligned and put them directly above or underneath each other. If I plug 1 in, we'll get I hat plus 3j hat. Plugging 2 in, we'll get 2I hat. And then plugging 2 in for the y component, or the j component, we get 0. So I don't need to write anything there. And then if I plug 3 in, we'll get 3I hat. And for the next value, we'll get minus 5j hat. All right, so now let's draw these. So the convention is typically that when we draw a position vector, that we draw the tail at the origin. So if I draw the vector r of a -1, so negative I hat plus 3j hat, if I draw it starting at the origin, that is actually going to perfectly go to where this point was on the curve where we were when t equaled -1. So that is the vector r of -1. The head will be at where the particle is on the curve at that time, in this case at -1. R0 is 4j hat, that's completely vertical. Completely vertical, and the head again will land on this curve, and that's r of 0. R1, if we draw that in, that's where the particle was after 1 second, so that's r of 1. R of 2 is 2I hat, so that's completely to the right. That's r of 2. And then r of 3 would be, so 3I hat minus 5j hat. I might need to draw a little bit more of the curve. That's somewhere here. R of 3, so let's extend the curve a little bit. Let's extend it down. Okay, so the head of this vector will land on the curve. So the difference between just a parametric equation and this vector valued function is, with the parametric function, that just describes all the points on this curve. The vector function, although it's closely related, describes vectors. Vectors such that when we draw them with their tails at the origin, the head of the vector lies on that curve. So they're both related because they both relate to the curve, but parametric gives us the points, the vector function gives us vectors. So in terms of our goals for this section, we have now done our first goal. We've talked about what a vector function is and how we plot them. In the next video, we will talk about how we take the derivative of a vector function and what that means graphically.